Hello everyone, so today I am here to make a video on one of the most powerful tool in linear algebra, and the topic is singular value decomposition. We can also call it SVD. So if you have ever wondered how Netflix recommends the movies, how photos are being compressed without lowering its quality, and how scientists reduce the dimension of huge data set, SVD is the secret sauce behind it. So in this video we will cover the theory part, break down the mathematical problem, and also implement it in Python. You might be wondering, what is singular value decomposition? Singular value decomposition is a way to break down any matrices into three simpler matrices, and it is very important in data science, machine learning, image compression, and even in noise reduction. Let's talk about the definition of SVD. So for any m into n matrix A, we can write A is equals to U matrix and sigma with, in this formula, U is called the U matrix, which is the orthogonal matrix, and the columns in this are called left singular vectors, and the sigma is a diagonal matrix, and the diagonal entries are also called the singular values. And V is another orthogonal matrix where its columns are the right singular vectors, and the V power T means V transpose. So the formula A is equals to U matrix sigma V transpose means that any matrix can be decomposed into three parts: a rotation, a scaling, and another rotation. Now let's talk about the applications of SVD. So first of all, it's image compression, and secondly noise reduction, and third solving linear systems, and fourth principal component analysis. So what is image compression? It means that it reduces the storage while keeping quality, and the noise reduction means it helps in removing the unwanted signals. And solving linear systems means even when they are unstable, it helps in solving linear systems. And last but not the least, principal component analysis. It's used for dimensionality reduction in machine learning. Let's see the mathematical example of SVD. Now our mission is to decompose this simple 2 by 2 matrix A into three parts: U, sigma, and V transpose. This is the SVD. We will go through this step by step. Now the first step is to compute A transpose A. Since our matrix A is symmetric, meaning it looks the same across its diagonal, a transpose is actually equal to A itself. So we just multiply A by itself. Doing the matrix multiplication gives us this result: 10, 6 by 6, 10. We need this matrix because its eigenvalues and eigenvectors will directly give us the next parts of the puzzle. Now we find the eigenvalue of A transpose A. We do this by setting up the characteristic equation. We subtract lambda from the diagonal elements and set to the determinant to 0. Calculating this determinant gives us 10 lambda squared minus 6 times 6, which is 36. So our equation is 10 minus lambda over 2 minus 36 is equals to 0. Now let's expand the equation. The quadratic formula gives us 20 plus or minus the square root of 400 minus 256, which is the square root of 144 or 12. So lambda is 20 plus minus 12 divided by 2. This gives us the two eigenvalue: lambda 1 is equal to 16 and lambda 2 is equal to 4. These are crucial because the singular values sigma are the square root of the eigenvalues. Now, to find the eigenvalues of A transpose A, the singular values, which is straightforward: sigma 1 is the square root of 16, which is 4. Sigma 2 is the square root of 4, which is 2. So our matrix will be the diagonal matrix with 4 and 2. We find the eigenvalue of A transpose A. For each eigenvalue, these form our V matrix. For lambda is equals to 16, solving the equation gives the both components of the vectors are equal. The unit vector is 1 divided by root 2 divided by 1 divided by root 2. For lambda 2 is equals to 4, the equation tells us the first component is the negative of the second. The unit vector is minus 1 divided by root 2, 1 divided by root 2. Now for the U matrix, because our original matrix A is symmetric, the process for finding U is very similar. The column of U are the eigenvector of A transpose A, but in this special case, it closes mirrors V. From this problem, U turns out to be this matrix. Notice that it's almost the same as V, but with a sign change in the second column. It's important to know that sometimes the signs can be different, but what matters is that the product U sigma V transpose gives us back our original transpose A. And finally, the complete singular value decomposition. We have our original matrix A equals to U times sigma, the diagonal matrix of singular values, times V transpose. This is the final part of our manual calculation. U and V are the rotation reflection matrix and sigma is the stretching matrix. Now let's move toward the Now let's talk about the implementation of SVD in Python. So here you can see the implementation code. Okay, and first of all we have imported the NumPy. We are importing NumPy, which is Python's calculator for math and matrices. And here this is the same matrix we worked on paper. We are creating it and showing it in our screen so we can see our starting point. And here you can see this line. This line does all the work. So the SVD function takes our matrix and returns the three pieces we need, like the U and the singular values and the V transpose matrix. And this all we are printing out the result. The singular values are exactly 4, 2, just like we calculated in the copy before. And here you can see that this code, this function gives us singular values as a simple list 4, 2. We need to convert this into a proper diagonal matrix for multiplication. And this code, in this code we have put the pieces back together, U times sigma times V transpose. This gives us our original matrix back. So this code reflects the quality check. It compares the original with our reconstructed matrix, and if they are essentially the same, it says true. Okay, you can also see it here. It says true. So if you look at the result of the example 1 matrix, you can see the singular values match exactly what we calculated 4 and 2, and the construction check also says true, which means our manual math was spot on. This shows that the Python confirms everything we did by hand. The computer does in one line what took us several steps, but understanding the steps help us know what's happening inside it. Now let's talk about the example 2. So here we are moving to a more realistic example, a 3 by 2 rectangular matrix. This is the kind of shape we often see with the real-time data. And here we are doing the SVD again, but if you notice the code, you can see full matrix is equals to false here. This gives us a more compact result for non-square matrix. It's more efficient. And if you see this code,
You can see the two singular values, one is large and one is tiny. This tells us that the matrix is almost rank -1. And this code here means we are going to keep only the most important part, just the first singular value and its corresponding vectors. And this part here describes about the slicing our matrices. To keep only the first component, we take the first column of U and the first singular value and the first row of B transpose. And this code explains that now we can rebuild the matrix using only these pieces. This is our simplified compressed version. And this code measures how much we lost by throwing away the small singular value. The errors should be about the same size as the values we discarded. And now if you see the output of this code in example 2, you can see the first value is 9.5 and the second value is 0.5. That means the tiny second value means the part of the data isn't very important. We are going to be bold and keep only the most important part, just the first component. Now look how close this is to the original matrix. Even though we threw away half of the information, we still captured the main pattern. Now you can see the error is about 0.5, which is exactly the size of singular value we discarded. This isn't a coincidence, it's how the math works. So this is the output of example 2. And this is the magic of SPD. We can throw away the unimportant part of our data and still keep what matters. For a small matrix like this, the savings are small. But imagine 1,000 into 1,000 images. We could keep just 100 components instead of 1,000, reducing the size by 90% while keeping the image recognizable. So I hope you understand it. That's all for today from my side. Thank you for watching.